In this video, we will be discussing all the methods of preparation of alkenes from the NCERT textbook. Let's get started with the first method of preparation. So alkenes being prepared from alkynes, and whenever you are taking an alkyne and adding hydrogen on an alkyne, you are going to get an alkene. Now you might be wondering that does the reaction really stop here, because the alkene which is getting formed has a further ability to react with hydrogen. Hydrogen can add on the double bond of alkene and correspondingly and ultimately give you the corresponding alkane. So how do we stop the reaction at the alkene stage? So to stop the reaction at alkene stage, we need to use a catalyst, and that catalyst, the catalyst which was catalyzing the reaction of hydrogen addition on the alkyne, that catalyst will perform the first step, but the catalyst needs to be poisoned. That poisoned catalyst means it will reduce the activity of catalyst and it will stop the further reaction of alkene to alkyne. So a catalyst poison is used like sulfur or quinoline. So when you are using pelletized charcoal needs to be poisoned with either sulfur or quinoline, and if you are using this kind of poisoned catalyst, then hydrogen will add across the triple bond of alkyne. It will form the alkene, and the further reaction, the further hydrogenation to alkene will be stopped because the catalyst had been poisoned. The catalyst that we spoke of is called Lindlar's catalyst. So Lindlar's catalyst means, like I just said, it is pelletized charcoal which is poisoned with sulfur or quinoline, and this kind of hydrogen addition on an alkyne is going to give you the cis alkene. Okay, cis means the identical groups have to be on the same side of the double bond. If that was your double bond, then H and H, that is identical atoms, are on the same side of the double bond. You call it cis alkene. So Lindlar's catalyst will stop the hydrogenation of alkene to alkyne at the Lindlar's catalyst will stop hydrogenation at the alkene stage, and it will stop further hydrogenation to alkane. And with Lindlar's catalyst, what you are going to get is the cis alkene. And on the other hand, if you are taking sodium and liquid ammonia, then hydrogenation of alkyne is going to give you an alkene only, but this time it will give you the trans alkene. So sodium and liquid ammonia is another alternative for converting alkyne to alkene and stopping the reaction at the alkene stage and preventing further hydrogenation. But with sodium and liquid ammonia as your reagent, the alkene that you end up getting is the trans alkene. That is, identical atoms or identical groups will be on the opposite side of double bond. Okay, there's an example written here. So if you check, it is ethine, that is CH triple bond CH, undergoing hydrogenation in the presence of pelletized charcoal poisoned with quinoline or some sulfur compound. That hydrogen will add on the triple bond, make it ethene, and the reaction will stop at the ethene stage. This was Lindlar's catalyst. Now we are taking propine and hydrogen, and you are using Lindlar's catalyst. You will get the formation of propene, and the hydrogenation will be stopped at the alkene stage, and further hydrogenation to alkane will be avoided because you are using Lindlar's catalyst. Okay, so that was the first method of preparation of alkenes. Going ahead with the second method of preparation, that is alkyl halides. If you are taking an alkyl halide RX, now here they are not writing it as RX because you need to see the structure to understand the reaction. We are writing it as CH3, CH2 and X. So this is typically an ethyl halide that we have taken. So an alkyl halide, when you are making it react with alcoholic KOH, when you are heating it with alcoholic KOH, then what happens is the halogen atom leaves with hydrogen atom from the neighboring carbon atom. Understand this. There is a carbon atom here, it has the halogen atom. The neighboring carbon atom is this. So the halogen is going to leave with the hydrogen atom of neighboring carbon atom. So when the two of them are going to leave, you get HX. This will leave as HX. But when that leaves as HX, let us assume that there were 2 electrons here. So hydrogen took away its electron. Carbon took away one electron with it. There were two electrons here. So one electron taken by X and the other electron taken by carbon. So after HX is leaving, this carbon has one odd electron and this carbon also has an odd electron. The two of them are going to share their electrons and form a double bond between the two of them. Okay, so we are getting the formation of CH2 double bond CH2, and that is ethene. So we are getting the formation of ethene. HX was coming out, but that HX is going to react with KOH, and that HX reacting with KOH is going to form plus H2O and KBr as the final products. So that is the dehydrohalogenation reaction, that is you are removing hydrogen and halogen from an alkyl halide by making it react with alcoholic KOH. You need to be very careful with the condition here, because instead of alcoholic KOH, what if I give you aqueous KOH? Let's assume the same reaction, that is CH3, CH2 and X, make it react with but aqueous KOH. So when you make this react with aqueous KOH, the reaction is proceeding somewhat in this manner. OH replaces the halogen, so you get CH3, CH2, in place of X you get OH, and that X is going to go along with K, so plus you will have KX. So had it been aqueous KOH, then you get the replacement of X with OH, and what you get is the formation of an alcohol. This precisely being ethanol and the other part being KX. So with aqueous KOH you get the formation of alcohol, but with the help of alcoholic KOH you are getting the formation of ethene. Okay, so keep in mind alcoholic KOH is going to give you alkene, whereas aqueous KOH is going to give you the corresponding alcohol by replacing the X atom with OH group. Let's read what they've mentioned in this extract here. The nature of halogen atom and the alkyl group are going to determine the rate of reaction. It so happens that this particular dehydrohalogenation reaction is the quickest with iodine, a little slower with bromine, and the slowest with chlorine. Now you can explain it in different ways. The way I used to perceive it when I was a student was this, that see, the bond is going to be stronger if the atomic sizes are comparable. If the size difference between the two atoms is very large, then the bond is going to be weaker. Carbon is in the second period of the periodic table, so if carbon atom is big enough, then comparable to carbon atom, the size is the size of fluorine will be almost similar to that of carbon atom. The size of chlorine will be a little bigger, the size of bromine will be even bigger, and the size of iodine will be very big compared to that of carbon atom. So the size difference will be maximum between carbon and iodine. That is why the bond between carbon and iodine will be very weak. So the bond between carbon and iodine will break very easily, and because here if you check the reaction, you are breaking the bond between this carbon and halogen. If the carbon and halogen bond is breaking easily, the reaction will be faster for this case. And that is why the carbon iodine bond being the weakest, the carbon iodine bond will break easily and the reaction with iodine will be the quickest. So this is what I used to think when I was a student. But there's yet another explanation which says that a weaker base is a good leaving group. A weak base is a good leaving group. So is I minus really a weak base? See, when you talk of HI, HBr and HCl, it so happens that HI will be the strongest acid, HBr will be weaker, and HCl will be the weakest. If HI will be the strongest acid, then the conjugate base I minus will be the weakest. So I minus is a weaker base than Br minus, and Cl minus is the weakest base. I minus is the weakest base because HI was the strongest acid, and so on the sequence continues. So I minus is the weakest base, and because I minus is the weakest base, I minus will be the best leaving group out of iodine, Br and Cl. Okay, so the reaction is going to be the quickest with iodine, and you can take whatever explanation you want. You don't have to anyway write the explanation. You just have to keep that explanation in your mind, and whenever anyone asks you a question that which of the halogens is going to give you the fastest reaction, with some explanation in your head, you can say that iodine is the one which will give the fastest reaction with alcoholic KOH. That is, the fastest dehydrohalogenation will occur with iodine. And if you talk about the alkyl groups, the tertiary group is going to be the quickest. I mean, tertiary alkyl halide will be the quickest in reacting, then secondary, and then primary. The reason is inductive effect. So if halogen is attached with a tertiary carbon atom experiences inductive effect from 3 carbon atoms or 3 alkyl groups, and that is why the halogen atom is pushed to a larger extent in case of a tertiary alkane. In a secondary alkane, the push on the carbon atom, if say for example this is a secondary alkane, the push on the carbon atom is only from 2 carbon atoms, and that is why the halogen atom will experience a lesser push. So maximum push in tertiary alkyl halide makes tertiary alkyl halides the most reactive for the dehydrohalogenation reaction, and secondary and primary will be a little less reactive for the dehydrohalogenation reaction. Okay. Now with the dehydrohalogenation reaction, there is a Sadzev rule that we need to discuss. It's not given in the NCERT book, but we will discuss it along with this only. So if you talk of the Sadzev rule, see, when you talk of the Sadzev rule, you need to consider a compound like this. Now this compound is 2-chlorobutane. When you make 2-chlorobutane react with alcoholic KOH, it is obvious that the halogen atom will come out with a hydrogen atom from the neighboring carbon atom. So one possibility is that the chlorine atom here is going to come out with the hydrogen atom here, and the other possibility is that this chlorine atom can come out with the hydrogen atom here. Consider the orange possibility. The double bond will get formed between the 2 carbon atoms here, and the product which you will get will look like this. It will be CH2 double bond CH, single bond CH2, single bond CH3. And the blue possibility is going to have the structure like this. The double bond will be between the 2 carbon atoms here, and you will have CH3, CH double bond CH, single bond CH3. Okay. Now which of the two will be a favored product? Which of the two will be a major product? That will depend upon how many substitutions are there on the double bond. More number of substitutions on the double bond implies that more favorable will be the product. So if you check this compound, let's rewrite it in this manner. The carbon-carbon double bond is here. So we have a carbon-carbon double bond, and both of them have a hydrogen attached with it. What about the double bond here? So here the double bond can be made in this manner. We have a double bond C. Along with the double bond C, we have one group as the ethyl group, and there was one hydrogen atom along with it. And along with this carbon, we had 2 hydrogen atoms. Other than hydrogen atom, everything else will be counted as a substitution. So on the double bond here, how many substitutions do you have? Hydrogen is not a substitution. Even this is not, and this is not a substitution. So there is only one substitution that you are having on the carbon-carbon double bond. Let's check how many substitutions we have in this case. So on the carbon-carbon double bond, this is not and this is not a substitution. So the number of substitutions are 1 and 2. So we have 2 substitutions on the double bond here, and that is why this will be the more favored product and this will be the less favored product. We can say that this is the minor product and this blue one is the major product. So this is what your Sadzev rule is. The Sadzev rule tells you that if there are 2 or more possibilities for the positions of a double bond to get formed, then the more substituted double bond is going to be the favored product. That is your Sadzev rule, and Sadzev rule can be applied very efficiently in the reactions of dehydrohalogenation, that is the reactions where you are making an alkyl halide react with alcoholic KOH. The rule is going to be very helpful in yet another reaction which is going to come a little bit later, but yeah, that's the rule that you should keep in mind. That is, the more substituted double bond will be the favored product. Let's go ahead with the next reaction. The next reaction is going to prepare alkenes from vicinal dihalides. So let's write this product once again in a proper way. I mean the reactant in a proper way. So the reactant here is CH2Br, CH2Br. So it's like CH2, CH2. The remaining valency of the carbon atoms has been satisfied with bromine. So we can call it 1,2 dibromoethane. Okay, for all those who don't understand what are vicinal dihalides, dihalides means a compound on which there are two halogen atoms, and vicinal means the two halogen atoms have to be situated on two different carbon atoms. So this halogen is attached to this carbon atom, and this halogen is attached with this carbon atom. So the two halogen atoms are attached with different carbon atoms, and that is why you are calling it a vicinal dihalide. For this reaction to occur, the two halogen atoms have to be attached to adjacent carbon atoms only. This kind of a compound, when you make it heat with, when you heat it with zinc, there's no heating mentioned, but I guess there was heating mentioned in the reaction. So if you are heating this kind of a compound with zinc, zinc is going to take away the two bromine atoms along with it. It will form ZnBr2. The leftover carbon-carbon atoms, imagine that the bond here is breaking. Bromine atoms are taking away their electron with them, and the carbon atoms take their electrons. The carbon atoms will share electrons between themselves and form a double bond between them. So that will give rise to the formation of ethene. And like I said, ZnBr2 is going to come out. So this reaction, like we discussed, is going to be possible with vicinal dihalides, where the halogen atoms are attached with the adjacent carbon atoms only. You can check this example as well. So in this example, it is CH3, CHBr, CH2Br. If I write it properly, it is CH3, CH, a Br along with it. Then that CH is attached with CH2 and a Br along with that CH2 also. Make it react with zinc. Zinc will take away the two bromine atoms, and the place from where the bromine atoms are coming out, a double bond is going to get formed in that position. So you will get CH3, CH, double bond CH2, and that is your product right here. And ZnBr was coming out. ZnBr2 was coming out. So reaction of vicinal dihalide with zinc is going to give you the formation of alkenes. And yeah, that's your third reaction for the preparation of alkenes. Let's go ahead with one last reaction, and in this reaction also we are going to use the Sadzev rule. Initially, let's take a look at this reaction with simply a very basic compound. So when you are taking concentrated H2SO4 and making it react with an alcohol, see, concentrated H2SO4 is a dehydrating agent. Dehydrating agent means concentrated H2SO4, it simply and simply removes water. Water means H2O, and H2O means you can consider it as HOH. So if you are removing HOH from an alcohol, then from where exactly do you remove that HOH? OH will be removed from the carbon atom which is having that OH group, and hydrogen will come out from the adjacent carbon atom, just like dehydrohalogenation. So if OH comes out from this carbon atom, hydrogen will come out from the neighboring carbon atom. So when this H2O comes out, you will get the formation of a double bond between the two carbon atoms here. So you get CH2 double bond CH2, which is ethene, and that ethene is the final product, and this H2O comes out, which has been written right here. Okay, so that is the dehydrohalogenation reaction. You simply use concentrated H2SO4 at a high temperature and remove water from an alcohol, forming alkene. Let's take one more example, and okay, in fact, this is the application of Sadzev rule. Before that, let's take an example of propene. So to form propene, what we need is propan 2-ol, or propan 1-ol will also do. So CH3, CH2, CH2OH, this is propan 1-ol. So we will write that OH below CH2 here, and even this CH2 we will write it as CH and an H over here. So if you are making it react with concentrated H2SO4 at of course a high temperature, H2O will come out because H2SO4 was the dehydrating agent. So we will have plus H2O, and the double bond gets formed between the two carbon atoms here. So we will have CH3, CH double bond CH2. Okay, that's how we are forming propene. Even if you take propan 2-ol, propan 2-ol is going to give you CH3, CH, CH3, and there is an OH group on the second carbon atom. The terminal CH3 we can write it as CH2 single bond H. Make it react with concentrated H2SO4 and heating. So this H2O will come out as H2O only, and the double bond will get formed between the two carbon atoms here. So you have CH3, CH double bond CH2. Okay, so that's propene getting formed again. So whether you take propan 1-ol or propan 2-ol, making it react with concentrated H2SO4 is ultimately going to give you propene. Let's take the higher alcohol. Let's take one higher alcohol. That is, let's take butan 1-ol. Now butan 1-ol, 75% H2SO4. So 1, 2, 3, 4 carbon atoms. Butan 1-ol means OH is on the first, that is the terminal carbon atom. OH can come out along with the H here, and the double bond is getting formed between the two carbon atoms here. So that will give you the compound which looks like this. The double bond between the two carbon atoms here. This part remaining the way it was over here. So this is but1ene and the H2O which came out from here. Okay. Now what if we talk about butan 2-ol? See, we need to apply the Sage-Zeff rule again. So butan 2-ol means this time OH. If you check for that OH is on the first, second, third, fourth. It's on the second carbon atom. So that OH can come out with the hydrogen here, or that OH can come out from the hydrogen here. For the red case, the double bond will get formed in the center, and for the blue case, the double bond is getting formed at the terminal position. The blue case has been shown over here. Check this, the double bond getting formed at the terminal position, and the red case, that is OH leaving with the hydrogen atom from the left hand side, that double bond is getting formed in the middle position, which is this case. So the more substituted double bond, there shouldn't be a CH2 here, there should be only CH. Okay, so this is a more substituted double bond, and that is why it is a major product, whereas this one is having only one substitution on the double bond of ethyl, which is why this is a minor product. Okay, it's a simple application of the Sage-Zeff rule, and yeah, this is yet another example with which you have learned how to apply that Sage-Zeff rule. Okay, take one more example of that Sage-Zeff rule. Okay, here there is no Sage-Zeff rule. In fact, there is an additional result that you need to know. So read the first statement that has been written over here. The ease of dehydration of alcohols is in the order tertiary greater than secondary greater than primary. So why is a tertiary alcohol dehydrated in the easiest manner? The answer is very clear: inductive effect. If you talk of a tertiary alcohol, that is OH attached with a tertiary carbon atom. If you talk of a secondary alcohol, that is OH attached with a secondary carbon atom. And if you talk of a primary alcohol, that is OH attached with a primary carbon atom. Due to the inductive effect, the OH of a tertiary carbon atom is going to get maximum push. The OH of a secondary carbon atom is getting a push only from two alkyl groups, and the OH of a primary carbon atom is getting a push only from a single carbon atom. So it's only one alkyl group providing inductive effect to the carbon here, and that is why the push on this OH group is coming only from one carbon atom. The least push is on the primary alcohol, the maximum push on the tertiary alcohol. So the tertiary OH group, the OH group attached with a tertiary carbon atom, can come out in the easiest possible way, a little more difficult with secondary, and the most difficult with the primary. You can check that with the concentrations of H2SO4 that are required. You required 75% H2SO4 concentration for removing OH from a primary carbon atom, but in the second case, if you check, this OH is attached with a secondary carbon atom, because this carbon atom is attached with a carbon atom here and a carbon atom here. So it is a secondary carbon atom, and the OH here is getting a push from a secondary carbon atom, which is getting inductive effect from two alkyl groups. So that is why this OH can be taken out more easily, and you can check it with the concentration level of H2SO4. You require 75% H2SO4, that is a stronger reagent in the first, that is the primary alcohol case. The reagent need not be very strong in this case, 60% H2SO4, and even a temperature lower than the primary alcohol case can give you the formation of alkene. In a similar way, check this tertiary alcohol case. Let's write that compound properly. It is 2-methyl propan-2-ol. So propanol means 3 carbon atoms, and on the second carbon there is a methyl as well as OH. So there is a methyl group here, OH group here, CH3 here and CH3 here. This OH is attached with a tertiary carbon atom, so it can come out most easily compared to secondary and primary. So if you check the strength of H2SO4 here, it is 20%, that is the least, compared to 60% for secondary and 75% for primary. And the temperature is also the minimum for taking out OH from a tertiary alcohol. Okay, so tertiary alcohols are going to react the fastest, secondary will react a little slowly, and primary will be the most difficult to carry out the reaction with to carry out the dehydration reaction. Okay, so from here if you check the reaction, let's draw that compound again. CH3, C, it was a CH3 there, I know. There's an OH here. I will write it as CH2 single bond H. So you can take out H2O from here, and the double bond gets formed between the two carbon atoms here, giving you this compound, and that compound can be named as 1, 2, 3. So 2-methyl. Then it is propene. You need not separately write prop-1-ene. That's a wrong way of naming it. The NCERT has named it in an incorrect manner. You need to name it as 2-methyl, not prop-1-ene, but simply propene. Because there's nothing like prop-2-ene. If there's propene, it has to be prop-1-ene only. There's no other possibility of propene being written in any other way. So this is simply 2-methyl propene. And yes, this is where we are done with the reactions of alkenes. See you in the next video where this is where we are done with the methods of preparations of alkenes. See you in the next video where we will be discussing the reactions of alkenes.